alternating series, and absolute and conditional convergence. All right, absolute convergence. Suppose we have a series u sub k. We say that this series converges absolutely if the new series, where the terms are the absolute values of our u sub k's, converges. And this is very nice because there is a nice little theorem out there that says if a series converges absolutely, then it converges. So let's see how we'd use that. Suppose we have this series 1 minus 1/2 minus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the fourth and so forth converge or diverge. Now this is not an alternating series because it doesn't go minus, plus, minus, plus. So what we need to do here is look at the absolute value of the terms and see what that series does. Well, if we look at the absolute value of each term, that just ends up being the series of 1 over 2 raised to the k minus 1. And that's a convergent geometric series. So that means our original series must converge as well. All right, let's use this theorem to show that the series cosine of k over k squared also converges. Well, our series is cosine k over k squared. And notice that if I take the absolute value of the terms, they're always going to be less than or equal to 1 over k squared because the absolute value of cosine k is less than or equal to 1. Now this series, 1 over k squared, is a convergent p-series. So by the comparison test, we know that the series, the absolute value of cosine k divided by k squared converges. Since that series converges, we can now say that our original series converges as well. All right, so now we have absolute convergence. Let's talk about conditional convergence. Let's consider that alternating harmonic series we saw, which was -1 to the k plus 1 times 1 over k. And we said that this series converges by the alternating series test. But it's not absolutely convergent because if we took the absolute values of each of the terms, we'd end up with the harmonic series. And we know the harmonic series diverges. Series like this are called conditionally convergent. So they converge absolutely, but not normally. So here's a nice test. It's called the ratio test for absolute convergence, but really it's just your ratio test taken on the absolute values of each of your terms. So what the ratio test for absolute convergence says is suppose you have a series with non-zero terms. And suppose the limit as k goes to infinity of the ratio of your k plus first term over your kth term and their absolute value is equal to rho. If rho is less than 1, the series converges absolutely. If rho is greater than 1 or infinity, the series diverges. And if rho is equal to 1, we don't know. The series might converge or it might diverge. So let's do an example. Let's look at this alternating series, -1 to the k times 2 to the k over k factorial. Now this is going to converge absolutely since rho, which is going to be equal to the limit of our k plus first term over our kth term, without the -1 because we're looking at the absolute value, that's equal to, when we simplify, that becomes 2 over k plus 1, and as k goes to infinity, the whole thing goes to 0. So we get that rho is less than 1. Now, this is just an FYI. It's really important. If we have a series, we can't always rearrange the order of the terms and get the same sum. So if I have a series and I change the order, I might end up with a different number in the end. That's really weird. That's probably one of the weirdest things I've heard, but it's really definitely true. I bet if you went and looked in your textbook, they'd give you a great example of that. So when can you rearrange the order of the terms? Well, it turns out that if you have a series that converges absolutely and you rearrange the terms, then that new series of the rearranged terms is going to be equal to the sum of your original series. So if you have absolute convergence, you can do all the rearranging you want.